To the chapter 12 homework. It was due on the 8th. I think I made that end up due on the 10th because we had some issues go on in the district. So there's a lot of different things here. You do need to put some good thought into things. You also need to make sure you're referring back to your understanding of linear motion sometimes and then relating that to rotational motion. So the first problem was problem 13. It was saying there's four masses as shown in this diagram connected by massless rigid rods, and so find the coordinates of the center of mass. So in the x direction, I've got 200 grams here at 10 centimeters, another 200 grams at 10 centimeters in the x direction. This 200 and this 100 grams are at 0 centimeters in the x direction, assuming this is my point of reference. So 200 times this, I initially screwed up and mixed my y's and x's up. So times 10 plus 200 times 10, all divided by the total mass of the system, end up giving me 5.71 centimeters. So that should make sense. It's a little more than halfway out because more of the mass is out there than at 0 centimeters. In the y direction, which is basically up this way, I've got 200 and 200 here, and they're 8 centimeters away from 0 centimeters in the y-axis, and then dividing by the whole mass. And again, this is a little over half of the way up of the 8 centimeters. So that's the center of mass coordinates. For part B, it's asking you to find the moment of inertia about an axis that passes through mass A and is perpendicular to the page. So I drew an X there indicating that this thing is going like a spear into the page, and then this whole thing would be rotating around it. So essentially, because this mass is at 0 centimeters, it would have no moment of inertia. This, and this would, based on the respective distances. So this is 8 centimeters away, this is 10 centimeters away, and this is 12.8 centimeters away. And we treat those like point sources, so that's mr squared. And I did a summation of all those things, and that gave me 0.00656 kilogram meters squared. Problem 18, you've got 30 newtons pulling on this disc at the top, 20 newtons on the bottom. This would cause a clockwise torque of 0.6 newton meters. This would cause a counterclockwise torque of 0.4 newton meters based on the diameter of being 4 centimeters. Convert that to meters, change it to the radius, because that's the distance that we are from the fulcrum, or from the axis, I guess. And so the net torque is 0.2 newton meters clockwise. Problem 24 basically gave you this graph, and it was a torque and time graph. You should be able to relate the fact that this is similar to the linear equivalent of a force time graph. And so it's asking, it says that this object has a moment of inertia of 4 kilogram meters squared and experiences the torque as shown in this graph. What's the angular velocity at 3 seconds? Assume it starts from rest. So the way you could do this is, if you think back to momentum and conservation of momentum, you could think about how the area of this graph would equal the impulse, which is a change in momentum. That's if you're thinking linearly. So if we're thinking rotationally, because this is torque instead of force, the area of a torque time graph would equal to the angular impulse, which is the change in angular momentum. And if we think linear like this, we think angular like this, this would allow us to figure out the change in angular velocity. And since we started off at rest, the change in angular velocity would be the same as our final angular velocity. So that is 0.5 radians per second. So the area is 1/2, 2 times 2, so that's 2 newton meter seconds. 2 newton meter seconds divided by 4 kilogram meters squared gives me 0.5 radians per second. Those units may not make sense. I came up with an alternate method, and that is if we look at this, this is the angular acceleration. And we can get angular acceleration by taking torque divided by moment of inertia. So basically we take whatever this number is, divide it by 4. So we're going from 0 to 0.5. Well, the area of this graph, or basically the integral of that, of a angular acceleration versus time graph, is equal to the change in angular velocity, much like how the area of an acceleration versus time graph is equal to the change in linear velocity. So that would be 0.5 radian per second. So the area of this graph would also give me my answer. For problem 31, you've got cat 2 here. I think there's cat food in this bowl and a cat down here. I didn't try to draw the cats because that was going to be horrible. So this is on a 4-meter long seesaw. The fulcrum's in the middle, 2 meters from either end. This cat's at this end, the food's at this end. So to stay balanced, the torques must be equal. So I think counterclockwise torque equals clockwise torque. Counterclockwise, 2 times 9.8, or G, times 2 meters, plus this cat, 4 kilograms for this cat, times however many meters times G, equals over on this side, 5 kilograms times 2 meters times G. Since G, or 9.8 newtons per meter, is on each side, that could cancel out to get my distance. So I get 4 plus 4x equals 10. I get that this cat would be 1.5 meters from the center. So it would actually end up being 0.5 meters from the end here. Yep, that makes sense. For problem 12 or 32, it says a car tire is 60 centimeters in diameter. The car is traveling at a speed of 20 meters per second. What's the angular velocity? That's just relating linear and angular. We've done that before, but you got to keep it in your brain. Yeah, meters per second divided by meters gives us per second. So then the speed at the top of this point would equal twice the average velocity, that's 40 meters per second. The speed at the bottom would equal 0 meters per second because it's in contact with the ground. So that had come up in our discussion. For problem 45, this one was asking about, you had a rotating rod, I believe, and it's asking about the angular momentum of this 500-gram rotating bar. Said it was going 120 RPMs, 2 meters long. So angular momentum is moment of inertia times omega, 1/12 ml squared, so that's the total length for this, for a rod being rotated about its center. So that's the moment of inertia. The angular velocity, well, if it's 120 revolutions per minute, there's 1 minute and 6 equals 60 seconds, times 2 pi radians over 1 revolution. That gives me this angular velocity. Multiply those two together, and my angular momentum is 2.09 kilogram meters squared per second. For number 62, this is actually a good problem. It's similar to one that I had in class. And what that means is we're trying to find the tension in this cable, and the torque clockwise would equal the torque counterclockwise for this, so this is a torque problem. And we're trying to figure out whether this cable will hold. It's rated at 15,000 newtons. So I'm going to pick this as my pivot point because the wall has an unknown force on it. I've got a person here. It's 80 kilograms at 2 meters from the end. I've got a beam here, 1,450 kilograms. That's 3 meters. Is that right? Yeah, it's 3 meters because it's a 6 meter long beam. Sorry, I'm trying to read my writing here. And we're trying to figure out basically the tension in this. So if we go torque counterclockwise equals torque clockwise, the counterclockwise is the force of tension acting at 6 meters because it's acting out here, times the sine of 30 degrees, because to find the torque we need the perpendicular component of force. The clockwise torque is basically the mass of the person times G times the fact that they're 4 meters from the fulcrum plus the mass of the beam times the fact that that mass is acting at the center of mass, which is 3 meters from the fulcrum, times G. So we end up doing all this stuff. We get that we have 45,766 newton meters of clockwise torque. That's going to equal this, which I'd said over here was our counterclockwise torque. So that says that the tension would have to be 15,255 newtons. So therefore, this person should be worried. The further they walk out from that fulcrum, the more stress they put on that support, that tension. And it's a lot different because this is at an angle, so the force has to be a lot since only a component of it is acting up. For number 69, we are looking at this problem similarly to how I had it explained one in class. I have 3 methods of solving this. I'm not going to go through all 3 methods, but I would like you to look at all 3 methods. So those are the 3 methods. I'm thinking of using net torque and moment of inertia to get angular acceleration and then relate that to linear acceleration. Here, I'm going to use torques and essentially use that, converting torques to forces and getting my linear acceleration from that. And then here I did my sort of cheat method where I'm essentially thinking of everything linearly and converting the mass of this disk to an equivalent mass as if it were acting in a straight line. So to find the time it takes this to go to the ground, we essentially need to find the acceleration. You've got 2 kilograms over here, 4 kilograms over here. You said you had said that there was friction exerted, so the friction caused a torque of 0.5 Newton meters. So normally this would rotate counterclockwise, so the torque is acting clockwise. So if we assume that that 0.5 Newton meters acts at the outside radius, it doesn't matter if it does or not, but we could say that torque is equal to force times the distance, and the radius is 0.06 meters, then that 0.5 Newton meters is the equivalent of 8.33 newtons being hung here on this as well, an extra 8.33 newtons. So that's the equivalent of the friction. If we go back to thinking in linear world, we have F net over M, but it's M equivalent. So 4 kilograms times 9.8 newtons per kilogram would cause a counterclockwise torque. 2 kilograms times 9.8 newtons per kilogram would cause a clockwise torque. That's subtracted because you're acting in opposite directions. And then you subtract the equivalent force caused by the torque related to friction. You normally would just divide that by the total mass, which is 4 plus 2 plus 2. But remember, this is a solid disk, and the pulley has a mass of 2 kilograms. And if it's a solid disk, the mass on average acts as if it is halfway from the center. So we think about that as being only 1 kilogram. So now I have a net force, equivalent mass, I get my linear acceleration, and then plug that into y equals 1/2 at squared. So 1.11 seconds. I do think it's going to be useful for you to look at some of these other methods. They all give you the same answer. The last one was problem 74. Problem 74 is a similar, or this is actually a parallel axis theorem problem because you rotate it about the edge of this thing, and the center of mass is here, and it's falling to the ground. It has a mass of 5 kilograms. It's a solid disk, so I equals 0.5 mr squared. And essentially, you want to find the initial angular acceleration. Well, that's net torque over total moment of inertia. So the net torque, 14.7 Newton meters. Why? Because the center of mass is acting here. It's 0.3 meters away. Gave you the mass, mg, at that distance. That's the torque. The total moment of inertia is equal to the moment of inertia if we rotated this about the center of mass plus the extra due to the fact that it's rotated along the edge. So the center of mass of a solid disk, 0.5 mr squared. The moment of inertia as related to the parallel axis theorem is md squared. And then that ends up giving us a total moment of inertia is 0.675 kilogram meters squared. Okay, so that's 21.8 radians per second squared. The second part is to find the angular velocity when it's directly below the axle. So this is going to be rotating around here. Now, so this actually is an energy problem, is the easiest way to think about it. EI equals EF, so you're going to have a loss of gravitational potential energy, a gain in kinetic rotational energy. I initially thought this would be a sum of rotational kinetic energy and linear kinetic energy. I'm still a little surprised at this, so this was not easy for me, but this was only rotating, and I think it's because this fixed point is not moving, maybe? At any rate, or maybe at that instant that the center of mass isn't moving vertically when it's at the bottom. But either way, this is only equal to kinetic rotational energy, so then we can get 6.6 radians per second. I found that tricky, and it still is not perfect in my mind. Anyhow, hope this helps.